Okay, today we're going to start the U substitution method for integration. This is the method that I've talked about several times in class that's going to make it easier for you if you don't see, for some of the integrals that we did on worksheet A, the ones that were a little bit more difficult and tricky that you kind of had to figure out using guess and check. This method is going to take the place of that if you don't immediately see how to undo the chain rule. So as I said, this method will undo the chain rule. It's more algebraic in nature. There are steps to follow. It requires us to make a substitution in the problem to change the variable. So if you remember that when we integrate, you have to have whatever variables inside your integrand, let's say it's a u, okay, then your d differential value that's here has to also be du. Remembering that these two have to match in order to integrate. Okay, that's important as we go through this because we'll have to change both the variable that's in the integrand and the differential variable over here from probably a dx to a du. The easiest way to demonstrate this is with an example. Okay. This takes practice. If you're not going to do the practice, this isn't going to get any easier. So going through, as we go through the examples, I'll give you some time to try to work ahead, and then we'll check the answer, or you can use the pause button, okay, to work ahead and then come back and check your answer. Alright, this is one that was like what was on worksheet A, and one that I said that if you didn't immediately just see the answer, that some of you were going to be able to do that, and that was fine. But if not, that we'd come up with a method for you to figure these out. Okay, this requires you to pick part of the integrand to be the u variable. Okay, so we're changing away from x's and we're going to be using u's instead. That's why we call it u substitution. Okay, so looking at the problem, okay, it's your choice. Really, we kind of in a fraction have two options. We can either pick the numerator as our u or the denominator as the u. Okay, as you see the method and as you go through examples, you'll get better at choosing your u based on your past experience with the method. Okay, I'm going to go ahead and pick the correct u so that we can see what the process looks like as we go through it the first time. Okay, so using my knowledge and my prior understanding of the method, I know that my best choice for u in this case is 4x to the third plus 7, the entire denominator. Okay. Looking at that u, the first thing I want to do is I want to take the derivative of it. Okay, so I've got u written as a function of x, so its derivative would be du dx. And the derivative of 4x to the third is 12x squared. The derivative of a constant is 0. Most likely, in the future, okay, we will always take this derivative in differential form, so multiply both sides by dx. Alright, looking at the original problem. The goal here is to have everything in this problem be in terms of u and du, so there are no more x's anywhere. Okay. The next step after you have this written in differential form is we need to figure out what dx is equal to. If I need to replace this dx in the problem, then this is a solvable equation, and I need to solve for dx over here. Okay, so to solve for dx, divide by, oops, wrong color, divide by 12x squared. Okay, so now I know that dx is equal to du over 12x squared. Alright, looking back at the original problem, okay, we now know what dx is equal to. So in for that yellow dx, I'm going to substitute in du is equal over 12x squared. Okay, again, looking back at the original problem, I also have this denominator, okay, that I'm going to substitute u in for. Let's make those substitutions and see what happens. Alright, so I've got the integral. The top is staying the same. Things changing there. This 4x to the third plus 7, that's our u, so we're replacing that with u. It's just substitution. The dx that's here, we now know that dx is equal to du over 12x squared. Okay, big hint for these problems. If you've done picked the right u, okay, when you look at this, you notice that the 12x squared from the top and the 12x squared from the bottom reduce. When you look at what's left over, you have 1 over u du. Okay, so now looking at the problem, we've just restructured it so that it's in an easier form for us to be able to investigate and look at, and hopefully you recognize that as it's something easy to integrate. Okay, as we know, the integral of 1 over u du would be the natural log of the opposite value of u plus c. Alright, looking at the differential equation. Okay, we're answering the original one that was in terms of x, so we can't leave our answer with the u in it. So now we know what u is. We set that up to begin with. We just take that u out and replace it with what we decided u was to start with. So u is 4x to the third plus 7. And then plus c. So that our final answer is in terms of x, not in terms of u. Okay, let's take a look at another example. Okay, looking at example 2, we have x to the fourth times the square root of 3x to the fifth minus 8 dx. Okay, again, looking at this problem, it's got factors, remembering that one thing we can't do is we cannot take the integral of the first factor times the integral of the second one. So in this case, again, we want to make a substitution to simplify this problem. Okay, again, using, okay, takes experience. You'll find that often you use the entire denominator to be u. Okay, in the terms of square roots or radicals, you'll use the entire radicand as u very often. Okay, so I'm going to choose that to try. Okay, so u is going to be equal to 3x to the fifth minus 8. Okay, then take the derivative of that u, and I'm going to write my derivative in differential form. Du is equal to 15x to the fourth, derivative of negative 8 is 0, dx. So that then this is very easy to solve for dx. Divide both sides by 15x to the fourth, okay, and solve for dx. So dividing, I get 1 over 15x to the fourth du. Okay, you could here decide to write du over 15x to the fourth. That's acceptable as well. Alright, at this point I'm going to pause a little bit, and you might want to pause the video. I want you to try to take that information that you have here, okay, substitute into the original problem, and see what you get. Okay, if you need more time to make your substitutions, go ahead and pause the video, because the next thing that I'm going to show you is where you should end up after you've done the substitution. Okay, if you've done your substitution correctly, your problem should look like 1/15 times the integral of the square root of u du. Okay, you're correct if you have the 1/15 still inside the integral. You can go ahead and pull that out to the front as a constant. Alright, let's take a look at how we would get there, how we would get that answer. Turn off the spotlight. Alright, making substitutions, okay, looking at what dx is equal to. dx is equal to this quantity. Looking at where our u is, the underneath of that radical is equal to u. Okay, so those are the two pieces I'm going to substitute in. So I've got the integral of x to the fourth times the square root, and that radicand is my u, so now it's just the square root of u, times dx, which is 1 over 15 x to the fourth du. Okay, remember the goal here is to have everything written in terms of u so that there are no more x's. That's how you know if you're on the right track. Okay, looking at my problem, I see that I have an x to the fourth in the top. Oh, and look, there's an x to the fourth in the bottom. Those are an easy reducing. And then this 1/15 that's left here, that's a constant. It's your constant multiple so that you can pull that out into the front of your integral. And so now we have 1/15 times the integral of the square root of u du. This is a much easier thing to integrate than the original problem was. Okay, so that square root we want to write as the 1/2 power. So u to the 1/2 du. And then this is a power rule question where we can just add 1 to the exponent. That 1/15 just gets to hang out on the outside. Adding 1 to the exponent. Okay, 1 plus 1/2 is 3/2. Multiply by the reciprocal, so times 2/3. Don't forget plus c. Okay, yes, go ahead and multiply out those fractions. Okay, and in this case, you want to take that u out and put back in what it was equal to. So 2 times 1 is 2, 40/5, 15 times 3. U, instead of u, I'm going to rewrite it in terms of x. My u was equal to 3x to the 5th minus 8. And now it's raised to the 3/2 power. Okay. Plus c. Okay. Remember, you can check your answer, okay, by taking the derivative of this. Okay, if you take the derivative of this, use the chain rule, you should end up with that expression from the original integral. Okay, third example. Taking a look at how this works with trig functions. Okay, looking at the problem that I'm given, the integral of x secant of 5x squared tangent of 5x squared dx. The first thing that you may notice is that secant tangent is a perfect trig derivative. Okay, secant tangent is the derivative of secant. Okay, but this problem has a little bit extra in here. We've got an x in the front, and if we notice, the argument isn't just plain old x. Okay, so in this case, we probably want to make a u substitution. For trig functions, it's very common that it's the argument of the trig function that you use as u. Okay, so looking at u, I'm going to let u equal 5x squared. Alright, at this point, see if you can take the derivative, solve for dx, and make your substitution. Give you a couple seconds to do that, and I'll show you where you should end up if you've done it correctly. Okay, at this point, if you're not done, go ahead and pause the video, finish it out so that then you can compare your answer to what you should get. Okay, if you've done your substitution correctly, you should get 1/10 times the integral of secant of u, tangent of u, du. Alright, let's take a look at how we get there. Taking the derivative of our u statement, I'm going to write it in differential form. Derivative of u is du. Is equal to 10x dx. Solving that for dx, getting dx all by itself, divide both sides by 10x. So dx is equal to 1 over 10x du. Okay, looking at that information, making your substitutions, we've got a dx that's 1 over 10x du. Okay, and of course, our original argument, 5x squared, okay, everywhere it occurs is where we're going to put the u. Okay, so my original problem, integral of x secant of u, I'm going to drop the parentheses since it's just a u, tangent of 5x squared, but that's u, and then dx is equal to 1 over 10x du. Okay, again, works like magic. If you've done it correctly at this point, okay, your x's should reduce so that everything that's left only has a u in it. Okay, we'll see if that makes sense. Say if those x's are gone, I've got a secant u, a tangent of u, and du, that's great. And then this 1/10 is the constant multiple that just gets pulled out to the front. So that we have the integral 1/10 of the integral of secant u, tangent u, du. And that's really nice because that's a perfect trig derivative. We know that that's the derivative of secant of u. Don't forget your plus c. And again, for these, we don't want our answers in terms of u. We want our answers in terms of x. So take out that u and replace it with what you said u was equal to start with. So secant of 5x squared plus c. Again, if you want to check your answer, you just take this statement right here and take the derivative of it. When you do the chain rule correctly, you should end up with that. The practice problems for this beginning of u substitution are very similar to the 3 examples we've done today. The biggest thing I can tell you about u substitution is you have to be willing to try, pick something for you, try it, see if it works, and then if it doesn't, try and pick something else. Okay? As you do that, as you go through that process, and when you find out what works, you're going to get a better sense for the next time you do a similar problem as to what to pick for you. So in the beginning, it might take 1 or 2 tries to figure out what to use for you, and as you do this over and over, you will get better and faster at it. The entire rest of this unit, we are going to spend over a full week in class practicing this method, looking at different types of problems, whether they be trig integrals, exponential integrals, okay, going forward and looking at some additional techniques that may use u substitution and maybe the arc trig derivatives. Going forward, it takes practice.